Can you see me?
Yes, sir.
Okay, let's get started. Okay. So today what we're going to do is we're going to talk about integration of differential forms. And in fact, this is probably one of the most important reasons to introduce the idea of differential forms, because as we've seen, differential forms are not really new objects, right? They are essentially a subclass of tensors. They're fully antisymmetric 0R type tensors. So you might ask, why should we care about this particular subclass of tensors? Now, it turns out that this is the natural choice of objects to integrate on a manifold, okay, or on submanifolds. So this is probably the most important reason why we introduced differential forms to begin with. So let me explain why you need them in general. Okay, so let's start with something more basic. Okay, so suppose we wanted to define. So suppose we have a manifold M. Okay, this is the manifold, and we have a function f, which means that on this manifold, which means it takes us from points on the manifold to real numbers. Okay, and what we'd like to do is we'd like to perform an integration on of this function over the entire manifold. Okay, it seems like a very simple thing to do. So we would like a definition of integration of this function on this manifold M. And what we want is that this integration should not depend on any choice of coordinate system, right? Because the coordinate system, as we've seen, is secondary. Okay, the manifold and this assembly of points, right, is the main characteristic of the manifold. So if I want to define the integration, a naive choice might be something like this. You might say, why can't I do in some particular coordinate system? Why can't I just do integral of f dx1 dx2 dot 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 till dxn? Okay, you might say this is an integration on the manifold. Now, a couple of things is one is this is coordinate system dependent. Okay, because supposing I change my coordinate system, then I'm doing an integration over f dy1 dy2 dyn. So, and these two may not be equal, right? So these two may not be equal in general. It depends on what the Jacobian of the transformation is. Okay, and so you can clearly see that if you define your integration of this function on the manifold in this way, first of all, it would be coordinate system dependent because you need to give a clear definition and you have to choose some coordinate system in which to make the definition. And that means in some other coordinate system, this would not agree. Okay. So what you'd like is a definition which is coordinate system independent. So this doesn't cut it, right? And so you can see why the naive choice of this kind of integration will not work. Secondly, these coordinates are only defined over a particular patch. Okay, so how do you define integration over the entire manifold when you have multiple coordinate patches? Okay, even that is something that's not trivial. So it turns out that if you want to define integration, okay, so this is the problem with trying to define integration in this naive way. Okay, but it turns out that differential forms are natural objects which you can integrate over a manifold. Okay, and they will allow us to integrate arbitrary functions over a manifold. Roughly speaking, these differential forms give us on an n-dimensional manifold, capital M, non-vanishing n forms. Okay, that is a rank n form will give us an integration measure. Okay, so basically I will integrate this function f along with some integration measure, and the correct integration measure turns out to be an n form. Okay, and we need to define what we mean by this. Okay, what we mean by this combination and integrating them. But you can see that at least the objects that we're looking at, the function and the measure, if we somehow define it to be this n form, that n form is something that obviously is a tensor and therefore does not depend on a choice of coordinates. Okay, so this would be independent of any coordinate system. Yes.
Sir, what is this measure?
A measure is, so for example, when you're doing an integration like this, dx1 through dxn is the measure, right? It's like how I'm splitting up my integral to do this integration. Okay, so it's giving me some kind of volume on the space. Okay, that's what we mean by measure. Okay, so some kind of volume which we're using to integrate. Okay. Okay, so the basic idea is that an n forms on an n-dimensional manifold will give us this measure. Okay, so this is the most important idea. Okay, so why differential forms are useful? Because they will allow us to define this kind of integration. Okay. Okay, any other questions here? Okay. Now, one of the important things is before you can even define a notion of integration, it turns out that you need one precondition. Okay, and this precondition to defining integration on a manifold is that the manifold needs to be what is called an orientable manifold. Okay, so we need a definition of orientability, and then we need to understand why this is an important criteria for defining integration. So let me first give you an intuitive notion of what is meant by orientability. Okay, so let's imagine a cylinder. Okay, so imagine a cylinder. So this is a 2D surface. Okay, the surface of the cylinder. Every point, okay, on this surface of the cylinder is a point on this 2D manifold. Okay, one way to obtain this 2D cylinder is to think of a rectangle like this. Okay, where I identify opposite sides. Okay, and I glue them together by preserving their orientations. Okay, so I preserve the orientations here and I glue them here. Okay, so I wrap it around and I glue it. Okay, so that gives me a cylinder. So a cylinder has a well-defined, you can think of it now if by embedding it in 3 dimensions, that there's a well-defined inside of the cylinder and there's a well-defined outside of the cylinder. Okay, so of course this is an ideal cylinder is only a collection of points. Okay, but if you take a sheet of paper and you imagine doing this, right, then there's an inside of the paper and then there's an outside of the paper. So there's an inside of the cylinder, then there's an outside, and these two are well separated notions. Okay, what do you mean by the inside and what do you mean by the outside? So for example, if I color the back of this paper red and the front of the paper green, okay, then let's say the outside of the cylinder will be green and the inside will be red. Okay, that's what would happen. Now what you can do is something interesting. You can create a different kind of surface by gluing together this rectangle in a different way. Okay, so you take the same rectangle, but instead of gluing them together by preserving these orientations, okay, of these two opposite sides, what you can do is you can flip the orientation. That is, you can put a twist in this, okay, and you glue it together such that this point and this point are glued together. Okay, so this point is A, this point is A, and if this point is B, then this point is B. Okay, so you glue it together by putting a twist in the sheet of paper. Okay, and what you can do is, so you twist the paper like this. So imagine literally taking a rectangle and then you twist it. Okay, you twist one end. So if I twist it, it looks like this. This is the twist in the middle, and this is now. So one thing you would see is if I colored one side red and the other side green. Okay, so this side would be red, but now here you can imagine that it's sort of green. Okay, as I go over here, and behind this is red. Okay, so this is what has happened after I've twisted it, and now I will glue them together. Okay, I will glue them together, and now I preserve the orientations and I glue it together. Okay, so what you get is what is called a Mobius strip. Okay, this is a different 2D manifold compared to the cylinder. Okay, it's a different 2D manifold. But now one consequence of this is that there is now not going to be, because now the green and the red are glued together over here. Okay. In fact, there's not going to be a well-defined notion of an inside and an outside. Okay. In fact, the Mobius strip will only have one side. Okay. And it'll transition from red to green and then back from green to red. Okay. But it'll transition sort of abruptly. So if I just imagine following this from what I think is the outside. When I come here, okay, I'll make a transition, okay, from red to green, and so I will not perpetually stay on the red side, okay, of this rectangle. I will switch from the red to the green. So there is no really well-defined way to say that one side is the inside and one side is the outside. Okay, so the inside and outside of a Mobius strip cannot be defined in this way. So intuitively, okay, our intuitive notion of orientability means that the cylinder is an orientable surface. That is, it has an inside and an outside. And a Mobius strip is a non-orientable surface. That is, you can't say what is the inside, what is the outside. Okay, there's only one side to it. Okay. Okay, is this idea clear?
So inside and outside are just like decided on the basis of the color of the surface, right? We are not even considering the volume that is enclosed by the cylinder, or we're not even looking at that. We're just the surface, which surface is inside, which surface is outside, right?
Right. Now, that's a good point. Okay, so obviously you see that there's one problem with this, which is when I just generally think of a collection of points, right? The points don't have sides to them. A sheet of paper has sides to it, right? But an idealized surface, which is just points, doesn't have sides to it. Okay, so so this notion of inside and outside works, and when I think about a sheet of paper and what I mean by orientability, and as you're saying, it doesn't depend. I mean, the other thing is I'm thinking about embedding this 2D sheet in 3D, right? And then I can imagine putting this twist and so on. Okay, and therefore I have this inside and outside means like what is, then it's sort of related to, thinking about it in 3D. I mean, imagining like a thickness to this paper and thinking about one thing being on one side and one thing being on the other side. Okay, so this notion of orientability is obviously only intuitively correct. But if we want to define it precisely for a manifold in a way that does not rely on either the embedding, okay, the fact that this is embedded in 3 dimensions, okay, or the fact that it's just a collection of points, right? So it's just a collection of points with no intrinsic notion of what is a side to them. So we need to define some kind of other notion of orientability, which agrees with this intuitive notion for a Mobius strip, but can be generalized to arbitrary manifolds. Does that make sense?
But how do I imagine this without embedding the color of 2 different sides? How do I imagine this?
Yeah, we'll see. I'll come to that. Okay, I'll
Okay.
give you a formal definition which will encompass this example.
Okay.
Okay, so this notion of sides, this in and out, kind of relies on this embedding in 3D. Okay, so this is exactly what we want to do. Is there a definition of orientability that is independent of an embedding? Okay, so we'd like to provide such a definition. So that's what we're going to do next. Okay, so we're going to give a definition of orientation of a manifold. Okay, so here is the idea. So let's start with the manifold M. And one important assumption is we'll assume this is a connected manifold. That is, it's not disconnected pieces. Okay. So for a connected n-dimensional manifold, there will be a well-defined criteria of what we mean by for orientability. But to define orientability, first we need to define an orientation. Okay. So so imagine that this manifold has some various coordinate charts or coordinate patches UI, okay, on the manifold. So there's a manifold M and various coordinate patches, let's say U1, U2, and so on, okay, which cover the manifold. And now imagine some point in the intersection of UI and UJ, okay, and this is the point P. And now imagine the tangent space at P. Okay, so these are tangent vectors in the tangent space TP of M. And these tangent vectors are spanned by either I can think of the coordinate basis vectors for this tangent space using the coordinates of UI, okay, in which case they would be something like partial x mu, where x mu are the coordinates on this patch. Or alternatively, I could use the coordinates on this patch if I call them y mu, okay, and to define coordinate basis vectors which are partial y mu. Okay, so these y mu are the coordinates on uj, x mu are the coordinates on ui. So these are two different ways of expressing the tangent vector, the basis of tangent vectors, the collection of basis tangent vectors. And we know now that there's a relationship between these basis vectors, okay, which is that these twiddle basis vectors, which are defined on the coordinate patch uj, are related by a Jacobian transformation to the tangent basis vectors on expressed using this x mu coordinates. Okay, so it's just expressed like this. This is partial y alpha is equal to partial y alpha x mu partial x mu. Okay, where here the thing we're holding fixed is all the other y's except all the y's are being held fixed here. Okay, when we're sorry, not the y's, the x's except for x mu, okay, are being held fixed. Okay, so this is the Jacobian, okay, of this transformation. So this is straightforward. Okay, now what we can do is we can define something called the Jacobian. Okay, the determinant of this Jacobian. Okay, this is a Jacobian matrix. So the Jacobian is the determinant of this matrix. So we define the determinant of partial x mu partial y alpha. And if this Jacobian is greater than 0, okay, for all points P which belong to that intersection. So if I take ui, uj, and all points P in the intersection, and for all points P in this intersection, if the determinant of J is greater than 0, then we say that the basis vectors EU and the basis vectors E twiddle U define the same orientation on the intersection UI, UJ. Okay, so what we mean by that is, let's say in the basis of UI, we had the tangent vectors, which were these E's, okay, E1, E2, okay. In the basis of UJ, sorry, not twiddle, okay, just the ordinary E's. E1, E2. And at the same point, okay, we had the basis vectors of Uj, which we denote as, let's say, E1 twiddle, E2 twiddle. Okay, and what we can do is we can construct the Jacobian that relates E1 twiddle can be expressed as some Jacobian matrix multiplying E1 and E2. Okay, so EI can be expressed as some Jacobian matrix multiplying the EJs. And now what we're saying is if the determinant of this matrix is positive, and it's positive not just at this point, okay, this point P, but at all points in the intersection of UI and UJ, then we say that these basis vectors, this collection of basis vectors, either this collection or this collection, okay, when I compare them, they have the same orientation. Okay, that's a definition that we're giving to what we mean by same orientation. And if this Jacobian is less than 0, that determinant is less than 0, then we say that they define an opposite orientation. Okay, these basis vectors give an opposite orientation, have an opposite orientation relative to each other. Okay, is this clear? So we'll see how this definition relates to what we had in the Mobius strip, but this is for now the moment of, right now it's the definition of just what we mean by orientation of the tangent vector space. Okay. Or sorry, it's the orientation of two coordinate patches. Okay, are these coordinate patches, do they have the same orientation or do they have opposite orientations? Okay. So let me give you an example. Okay, so for example, let's take R2. Okay, and we take so with standard coordinates x, y, and we define partial x and partial y. Now we could have also taken a rotated coordinate system, okay, which is x prime, y prime, in which case we'd have got the basis vectors partial x prime, partial y prime. Okay, and so if our x and y are related by a rotation, then the coordinates are related like this: x prime, y prime, okay, is equal to cosine theta minus sine theta, cosine theta, where this is the angle of rotation times xy. And then I can find out the relationship between these basis vectors, okay, using the Jacobian. So partial x prime, partial y prime is going to be the inverse of this matrix: cosine theta, sine theta minus sine theta, cos theta. Okay, acting on partial x, partial y. So it's basically a linear superposition of these. You worked this out before, right? Much earlier in the course. So the Jacobian is this matrix. Okay, so this is basically the partial x prime. Okay, and now the determinant of the Jacobian, which is the determinant of this matrix, is cosine square theta plus sine square theta, which is 1 in this case. Okay, so in this case, we would say that both the old basis vectors, that is this combination, and the new combination, that is these ones, okay, they define the same orientation. And since this is going to be true everywhere on the manifold, okay, then we say that both coordinate systems, okay, both coordinate patches, in this case, the coordinate patch covers the entire manifold. Both these coordinate patches define the same orientation, okay, on the manifold. So that is these basis vectors and these basis vectors at all points P on this intersection or over the entire manifold define the same orientation. Okay. Now, what would be an opposite orientation? So imagine like a parity flip like this. Okay. So imagine that instead of I had something like x prime, y prime, my new coordinates are related by, now I flip the x-axis. Okay, so this is my x prime, y prime, as opposed to my original xy, which look like this. So this is a parity flip. Okay, and if I look at this parity flip now, again, so now I have partial x, partial y like this, but now my partial x prime, partial y prime looks like this. Okay, these are these direction vectors. Now, what has basically happened is that you flip from a right-handed coordinate system to a left-handed coordinate system. But again, this notion of right-handed and left-handed has to do with embedding in 3 dimensions, because I think of the cross product, okay, of x and y, and the cross product using the right-hand rule points in the plus z direction, versus the cross product of this x and this y points in the minus z direction. And basically, how do we decide whether that, how do we decide on a general orientation without thinking of embedding in higher dimensions? Well, we do exactly this. We take the determinant of this Jacobian. Okay. So we now construct partial x prime, partial y prime. We find that it would be -1, 0, 0, 1, partial x, partial y. This is the Jacobian. In this case, the determinant of this Jacobian is -1. Okay. So now we say that these two basis vectors, okay, they define opposite orientations. And if this is now true over the entire overlap of these coordinate patches, so the x prime, y prime cover the entire space, x, y cover the entire space, and in their overlap, everywhere in the overlap, these have an opposite orientation. Okay. So so basically the point is that now this definition of handedness, that is left-handed or right-handed, that is of course specific to 3D, okay, or the embedding in 3 dimensions. But the definition of orientation that we have given, okay, is more general. This is the definition of orientation which relies only on the determinant of the Jacobian and therefore can be extended to any number of dimensions. In 3 dimensions or in 2 dimensions, okay, it happens to agree with our notion of cross products, okay, and thinking about right-handed and left-handed coordinate systems. Okay, any questions here?
Okay, this determinant thing, did we derive, not derive, did we look at this from our notion of orientability from 3 dimension? Like we know that some that is inside and that is outside. Then we checked the determinants and then we saw that they were positive and negative, or was it derived from something else? Like did we go from that there? We checked
I
it.
understand. Are you asking historically how did we figure out that the determinant is the right thing to look at?
Yes.
I don't know historically how this was done, but I guess yes, inspired by that. Yeah.
Okay.
Yeah. Okay. Okay, so now what we'll do is we'll give a definition of orientability of the manifold. Okay, so now that we have a definition of what we mean by same orientation and opposite orientation of 2 coordinate patches. Okay, now what we can do and coordinates on 2 different coordinate patches. Okay, we can define orientability of the manifold as a whole. Okay, whether a manifold as a whole is orientable or not. So if M is a connected manifold covered by some UIs, okay, so this is M, and now we have a collection of coordinate patches which cover the entire space. Okay, so this is UI. M is said to be orientable if for every overlapping pair, okay, if you take every overlapping pair UI and UJ, then there exists local coordinates x mu on the UI and y mu on the UJ. So that is, if I take any pair, I can find a set of coordinates x's on this pair, sorry, on this patch UI, and I can find a set of coordinates y mu on this patch, such that, okay, the Jacobian is positive. Okay, if I can find this, if I can find such a set of coordinates on every intersecting pair of intersecting patches, then I say that the manifold is orientable. Okay, that gives me a definition of what we mean by orientability. However, if M is non-orientable, okay, then we cannot find a coordinate system, okay, on every pair of intersecting patches. Okay, we cannot simultaneously find. So what that means is, so supposing I have 3 patches. Okay, let's say something like this. Okay, then I find X and I find Y. Okay, and on their intersection, this choice of coordinate system X and Y allows, let's say, U1 and U2 to have the same, let's call this U1 and U2, U1 and U2 to have the same orientation. But now with this choice Y, sorry, let's just do it like this. Okay, so now, so let's call this 1, 2, and 3, and we'll put a coordinate system Z on the third one. Okay, now we're free to choose X and Y and Z. We're free to choose the coordinate systems on these patches. The claim is, suppose I choose the coordinate systems on 1 and 2, such that everywhere in their intersection, okay, I find everywhere in their intersection, I find that the Jacobian is positive. Okay, then I would say that these coordinate systems X and Y on U1 and U2, they define the same orientation of U1 and U2. Okay, but now with this choice, okay, it may not be possible to find a coordinate system Z, okay, on patch 3, U3, such that, okay, the intersection of 2 and 3, okay, gives me, let's say, a positive Jacobian. Okay, or okay, let's suppose that you can find a positive intersection here. Okay, but then what will happen is then the Jacobian in the intersection of 1 and 3 will turn out to be negative, because basically this fixes this coordinate system, the demand. So once I fix X is an arbitrary choice. Y gets fixed by the demand that 1 and 2 must have the same same orientation. Okay. Then similarly, Z gets fixed by the fact that 2 and 3 must have the same orientation. And now I don't have the freedom to fix X or Z anymore. So I just have to ask, okay, do X and Z define the same orientation on the intersection of 1 and 3? Okay, and we might find that it does not. Okay, the Jacobian is not positive everywhere. Okay, maybe at some points it's negative. So in this case, we say that M is non-orientable. That is, J cannot be positive in all intersections of charts. Okay, so let's go back to our Mobius strip example and see how this happens. Okay, in the case of the Mobius strip. So our Mobius strip, okay, we thought of as, okay, so it's this rectangle. Okay, but now what we need to do is we need to assign unique coordinates to every point, and the coordinates need to be smooth. Okay, so naively I would say, let me put an x1 and x2 on the strip, but then you see that, for example, this point. Okay, so let's suppose this is at minus b on the minus a on the x-axis, and let's say plus b. Then the coordinates of this point, which is actually mapped to this point, would be at plus a, comma minus b. Okay, and I mean, so I cannot use just the same reason why on a circle you need two different coordinate patches. When I glue these ends together, okay, this point gets mapped to this point. Okay, and the coordinates change discontinuously. Okay, so if I don't want the coordinates to change discontinuously, I have to break this up into different coordinate patches and then talk about these different coordinate patches. So what we do is we break up the Mobius strip, okay, into two different coordinate patches. Okay, which is, let's say one patch has coordinates x, okay, which we denote as x1 and x2, and one patch has coordinates y, which we denote as y1 and y2. Okay, and this is half the Mobius strip. Okay, so it's something like, so we call this region of this patch B, and this region of this patch is A, and this region of this patch is A prime, and this region of this patch is B prime. And now when we glue them together, A and A prime are glued with the same orientation, that is, they're glued kind of this way. But B and B prime, when they're glued, are glued with the opposite orientation. Okay, so we glue them together like this. Okay, so now, and you glue them in a smooth way, okay, which means that actually this region, okay, of A prime, okay, this actually overlaps with this region of A. Okay, so there's an overlap of these two regions. And this region of B prime, okay, which is over here, this region of B prime smoothly overlaps with this region of B, but with opposite orientations. Okay, there's a twist, okay, in these regions. Okay, so now we glue A and A prime, but we twist B prime before joining it with B. Okay, so now on A and A prime, okay, on this intersection region, okay, of A and A prime. So if I call this coordinate patch U1, Okay, and this patch U2. Then the intersection of these two coordinate patches is kind of interesting. Okay, the intersection is either A, okay, because A and A prime are the same. Okay, it's the union of A and B. Okay, is the intersection of U1 and U2. Okay, because it's this region and this region that are overlapping between these two patches. Okay, so the intersection of U1 and U2 is A union B. Okay, this region A is the same as this region A prime. This region B is the same as this region B prime. Okay. Okay, so now on A and A prime, okay, that is on these regions. Okay, we have chosen our coordinates in such a way that x1 is equal to y1, x2 is equal to y2, right? Because they're smoothly glued. Okay, when you glue them together. And so the Jacobian obviously in this case will be 1, which is greater than 0. Okay, because y1, y2 is equal to 1, 1, 0, 0, x1, x2. And so the Jacobian will be the inverse of this matrix, and the determinant of that inverse of identity is identity, and the determinant of that will be 1. But now what you see is, so on part of A intersection A union B, which is A, okay, the Jacobian is positive. But on the other part, which is B, okay, I no longer have that freedom anymore. So on this intersection B and B prime, okay, since we put a twist, what we'll get is on this patch, that is on the patch B prime or the patch B, y1 will be equal to x1, but y2 will be equal to minus x2. Okay. Yeah, okay. So, okay, sorry. So maybe I should have put y1 this way. Okay, so what I will get is y1 will be equal to x1, but y2 will be equal to minus x2. Okay, and so what I will get is and in this case, the inverse of this matrix is the Jacobian, okay, and the determinant of that is the Jacobian, so the Jacobian will be minus 1. So you see that even though the coordinate systems, okay, I can choose the coordinate systems in such a way that in the intersection region A, okay, the Jacobian is positive, but then automatically in the intersection region B, the Jacobian is negative. Okay, I don't have the freedom anymore to choose my coordinate system now in this overlap region. So so what that is going to do is basically in the overlap region. Okay, I mean, so basically this will tell us that the Mobius strip is non-orientable according to this definition. Okay, so now if I think about tangent vectors and I think about what's going on with the tangent vector, so now instead of thinking about painting one side of a paper red or painting one side of a paper green, think about drawing basis vectors. Okay, so I've drawn basis dual vectors in this case, but we could have easily well thought of drawing basis vectors. So imagine dx dy, okay, and then dx dy. So I imagine like taking this dx dy at every point. Okay, I've defined what I mean by this dx dy. And roughly speaking, dx cross dy using the right hand rule, okay, gives me an outside. Okay, outside is dx cross dy, okay, which is the outside. And dy cross dx would give me the inside, okay, the inside direction. So I have an outside and I have an inside, at least local. Okay, but then what happens is as I go around this, okay, so I go on seeing that dy cross dx is out, dx cross dy is outside, outside, outside. But the problem will come when I come to this region with a twist and I cross over. Then what I would have found because of this twist, okay, dy would have gone negative. And if I use my definition of dx cross dy, dx cross dy is negative. So it's actually pointing inwards. Okay, so everything was outside, outside, outside. And then suddenly here it's pointing inside. Okay, and I've just continuously gone along, the same, along what I thought was the same side. Okay, and therefore over here is somewhere where I would have had to make a break, and this is the region where I glued together B and B prime. Okay, so and so there's a problem of I can glue them together still. Okay, but then I have to change how I define the gluing the gluing of coordinates. Okay, I can't use the same coordinate patch XY over the entire space. Okay, so now basically there's no well-defined notion of an inside and an outside, and this cross product dx cross dy, when I think about the outside, that is like thinking about red. Okay, and thinking about the inside is, so if I think about the Mobius strip this way. Okay, so imagine that I've glued these two together. Okay, so I've glued these two together, and now a cross product like this, okay, of two vectors defines the outside and the inside. Okay, the opposite orientation will define the inside. One orientation defines the outside. So roughly speaking, I'm using a cross product to define insides and outsides. And instead of the cross product, really what we're going to do is we're going to define really the wedge product. Okay, dx wedge dy. Okay, because this notion will not rely on a metric. Okay, and it will not rely on this notion will not rely on a metric. Okay, so and it won't rely on any kind of parallel transport or anything like that. Okay, this notion of this wedge product, okay, is basically the tensor product, fully antisymmetrized tensor product of differential forms. And this notion will agree with, okay, so this will allow us to define an outside and an inside, or equivalently, this notion can be related to this notion of the Jacobian, the determinant of J being positive or the determinant of J being negative. Okay, so dx cross dy outside, okay, that's what we had thought of as painted red, and dx cross dy negative is inside, that's what we had thought of as painted green. So this idea of painting one side or another can now be swapped for thinking about the sign of the cross product, okay, or as we'll see, the sign of the wedge product. Is this idea clear?
So can you explain once, like while flipping the B and B part, like how that minus sign comes?
In the coordinate transformation?
Yeah.
Yeah. So so let's say this is yeah, sorry. Okay, so maybe what I wanted is this. Okay. Yeah, okay, sorry. Let me be more precise, okay? So let's suppose this is really from something like, let's say, 0, -5 to 5, right, in this way. And let's say it's, let's say -1 to 1, okay? And it's -1 to 1 in the y direction as well. Okay, now what I want is, let's say I want to start gluing them together. Okay, so I mean, I was a bit flippant here. Okay, when I said y1 is equal to x1, y2 is equal to x2, I can of course do that. So let me choose my y1 so that it starts at this point. So let's suppose this region is 0.8. Okay, so I can imagine that my a prime starts at 0.8. This is my y coordinate. Okay, and my my next region is at 1. So now basically this is the same mapping, right? So in the region A, X and Y are exactly the same. X1 and X2 agree with Y1 and Y2. Do you agree with this?
Yes, sir.
Okay. And now let's imagine that this is at 1.8 and sorry, this is at 1.6 and this is at 1.8. Okay. So this is separated by, sorry, is it 2.8? 2.8 and 2.6. Okay, is this clear? So basically there's a separation of 2 still. Okay, but now this has coordinates at 2.6. Okay, and this is at coordinates 2.8. Okay, this is -1 to 1. So this is basically some different coordinates. I mean, of course, I'm free to choose what I chose for these coordinates, but let me choose it this way. All right. Is this fine?
Yes, sir.
Now the thing is, how am I gluing together B and B prime? I'm gluing them together in such a way that they have opposite orientations. Okay, in this region where they overlap. Okay, which means in this region of opposite orientations, I mean, of course, the gluing together has to be smooth, but let me just imagine a small enough region of B and B prime. So that now when I'm gluing them together, okay, what I'm saying is, let's say the y1 coordinate, okay, is equal to the x1, sorry, y1 is equal to, so I want this region to map to this region, okay, but sort of going this way. So y1 is equal to minus x1, 2.8 minus x1. Sorry, y1 minus 2.8 is equal to 1 minus x1. Sorry, minus 1 minus x1. Okay, so the basic idea is if x1 is equal to minus 1, then the right hand side is 0. If y1 is equal to 2.8, then the left hand side is 0. Okay, and that basically tells me that these points and these points, okay, have the same coordinates. Okay, but as I'm going this way, okay, is what I'm gluing with this way, right? So that's why there's a minus sign in front of the x1. Does this make sense so far?
Yes, sir. So when it's like in case of B patch, the leftmost one is glued with the rightmost of B primed.
Yes, this leftmost line, which is here, right, is glued with no, sorry. It's glued with this. Okay, so maybe I should correct this. Okay, so minus 1.8. Right, minus 2.6 is equal to, sorry, let me just take that back. Okay, so they're glued in exactly the same way. Is equal to, what do I want? X1 plus X1 and X1 minus minus 1. Okay, is this fine? So basically the difference of, so if I choose something which is at y1 minus 2.6, which is, let's say, over here. Okay, so this is telling me how far I've moved from this point at 2.6. This is now telling me how far I moved from x1 is minus 1. Okay, and those two are exactly the same. Is this part fine?
Yeah, yes, like.
And now the interesting thing will come for y2 and x2. Okay, because now y2 I will just set directly equal to minus x2. Okay, in the overlapping patch, I've twisted it so that this point will not map to this point. Okay, but rather it will map to this point. Is that okay?
Yes, sir. Like if I consider the B prime, the top bottom point of B prime is mapped to the top upper point of B. So that's why that minus.
Yeah, exactly. That's the twist that you put in it.
Yeah, this minus
Okay.
is exactly minus, but in the y1 x1 there are like other terms, so that's why.
Yeah,
The,
but okay. I mean, yes, these terms I was not very careful. Okay, I mean they will be present, but they don't affect the Jacobian, right?
yeah, Jacob this one.
Because the orientation will still be determined by this part.
The partial derivatives.
Yeah, there'll be some constants here, but they don't affect the Jacobian. Okay, so now we've defined a notion of what it means for an orientation to a manifold. Okay, and this notion of orientation agrees with our intuitive notion for what we mean by orientation. Okay, when we thought about Mobius strip versus cylinder. Okay, so if M is a connected manifold covered by UI, M is said to be orientable if for every overlapping pair, okay, there exists, you can find local coordinate systems, okay, such that for every intersection, okay, of ui and uj, the Jacobian is positive, okay, at every point in the intersections. Okay, then you say that the manifold is orientable. Now, orientability is very important for integrability. Okay, and the reason is obvious. Okay, because when I say, let's suppose if I do a 1D integration, okay, I will imagine that I do integral f dx, okay, along this, as I move along x. But now if I'm doing integration in a plane, for example, so if I have f of xy dx dy, okay, and here, I mean, I can think about orientability in terms of like what are my starting point of integration, okay, to my final point of integration, so from a to b. So I'm kind of integrating this way. Okay, this is my orientation. In 2D, okay, what do I mean by orientation? In 2D, what I mean by orientation is I usually think about a signed area element. Okay, think about an area element, that is this dx dy. And the sign of this area element defines my orientation. So is it positive orientation or negative orientation? And typically, if we think about this, then we're thinking about, let's say, some kind of counterclockwise orientation defined through a cross product. And similarly, I could have defined an opposite orientation. Okay. Now, this notion of an area element and having the sign of the area element defined, that does not generalize. Okay, if we think about cross products, but if we think about this determinant of the Jacobian, that is something that generalizes. Okay, and therefore this notion of orientability. Okay, which means how are we defining this integration? Are we which orientation are we defining it with? In order to define that, you need to have a notion of orientation for your manifold itself. Okay, so unless the manifold has an orientation, a well-defined orientation, that is, if I define an integration on a cylinder, I'm defining it either on the outside or on the inside, and I can say the integration over the inside is minus of what is on the outside. But on a Mobius strip, there is no such notion of integration that I can define. Okay, the reason is because there's no well-defined side, so the sign of the area element changes as I cross the Mobius strip. Okay, so we can't define integration on a Mobius strip, but you can define integration on a cylinder because there's a well-defined notion of orientation. So orientability of a manifold is the precondition that we need. Okay, that is, you need to satisfy that criteria that in the intersection of all charts, you can find coordinate systems that have positive Jacobian. If this is true, then the manifold is orientable. If it is orientable, then you can find then you can define integration on the manifold. Okay, so now if assuming that we have an orientable manifold, here's a conjecture, okay, and which we'll show in a moment is true. So if M is an n-dimensional orientable manifold, then there exists an n form. Okay, an n form is the maximal rank of a form that you can have, right? It's a 0R type tensor, which is fully antisymmetric in all the R lower indices. There's only one basis of such n forms. And this omega vanishes nowhere. Okay, then we want this n form on the manifold, which is non-zero everywhere on the manifold. We want to find. Okay, and basically the claim is that you can always find such an n form on an orientable manifold. Okay, it's not guaranteed. In fact, you will not be able to find it on a non-orientable manifold. Okay, so this n form, okay, that we find. Okay, this omega, which is an n form, this is called a volume element. Okay, we'll see why it's called a volume element. And this is the thing that plays the role of a measure when we want to integrate a smooth function f over the entire manifold. Okay, so the idea is clear. So we have an orientable manifold, M. And on this orientable manifold, we want to find a non-zero n form, that is an n form that is not zero anywhere. And this n form will allow us to now define an integration of functions by sort of using this n form as a measure. Okay. Any questions?
Sir, like the case of cylinder, we can if we draw a continuous curve on outer surface and looking it as embedded in 3-dimensional, then the curve will never pass through the inner surface. But in case of Mobius strip, if I continuously draw a curve, it will pass through both surfaces. So, um, is it due to that we cannot like embed the this strip into a three-dimensional? Or
No, you can embed it in 3 dimensions. There's no problem embedding it. You can literally take a sheet of paper and twist it and join it together, right? And that's embedded in 3 dimensions.
so,
Okay.
but in case of cylinder, when we pass through the one surface to other, I mean, it will be not discontinuous, but non-differentiable at that point.
No, okay. I mean, okay, strictly speaking, it's just a collection of points, right? So there is no notion of inside and out. So if you think about this, cylinder like this, right? As I go this way, I just come out from this side. Okay, and with a Mobius strip, it's as you go this way, you come out from here.
Yes.
I am not sure what else you are looking for. I mean, yeah, you can think of this as if I literally took a sheet of paper, then I would come out on the other side of the paper when coming out here.
Yeah. Like can we do this in like we do for the cylinder? Like one case is we are looking it from outward. Then the notion of right due to the coordinate right z, if I assume my z axis along the axis of I mean, the cylinder and draw the vector on tangent vector it's on its outer surface. And one case can be that I'm looking from inward and drawing the same tangent vector, but basis for this tangent vectors. But in that case, my orientation of x and y will be changed.
Sorry, I'm not getting the question exactly. Can you say that again?
How can we visualize this with Mobius strip that my like the coordinate basis tangent vectors? Like in case of cylinder, when I'm looking from them from outward, assuming my I mean right-handedness of the coordinate axis, then one case is that I'm looking from outward, then my cross product will be direct in different direction, and if I looking from inside, then cross product of these uh, axis will direct in opposite direction. So I mean, can we do this with Mobius strip in some higher dimension?
Okay, so again, you shouldn't think of the cross product, but you can think of the Jacobian. So in the right-handed coordinate system here, the Jacobian is positive. Okay, I still haven't fully got your question, but let me try to answer what I understood. So if I come out from this side, this is, let's say, the x, like, x hat, y hat. What will happen is that now my orientation would have flipped, okay, because of the way I've glued these coordinate systems together. So if I literally imagine transporting these around, they will come out like this, okay? And I mean, if I would literally drawn these on a sheet of paper as I was going around, this would come out on the back side of the sheet of paper, okay? So the front is red, the back is green, I would come out on the back side. Okay, and the way I know, another way to tell that I've come out on the back side is x cross y would be negative. Okay, but in either case, I mean, the point is that you can take either definition that you like, okay, for orientability. You can either for the case of the Mobius strip, because you can think about the embedding. So you can literally think about what is. I mean, even there, you can't really think about the inside and outside without defining some notion of a cross product. Okay, or this determinant. So. So it's only literally with a sheet of paper that you can really think about, painting one side red and one side green. The only natural notion on a general manifold is that you have to think about the cross product, or basically using all the basis vectors together, you define a Jacobian, which defines an orientation to your coordinate system. I'm sorry, I didn't completely understand your question still. I don't know if I've answered it.
Maybe I'm getting confused. Like in case of cylinder, we have this notion in 3 dimensions that tx cross dy will point in z direction.
Yes.
So
okay, let's just stop there. Okay, dx cross dy will point in the z direction. So if I draw tangent vectors on the cylinder, dx cross dy will point outwards. Yes.
yes, sir. And the same point I can draw from inside. I'm looking at from inside.
It doesn't matter which direction you look at it, right? Dx cross dy will always point this way. In 3 dimensions, dx cross dy always points in the same direction. It has nothing to do with how I look at the vectors.
So
right, I have to
this
still
thing-
use my right hand tool. So imagine looking in and imagine, so like now imagine that we're here and we're looking at this, right? Then what we'd see is this. Dx cross dy would be into the paper, but into the paper when I'm looking from inside the cylinder is the same direction.
And one way is that if I draw a curve from outside to inside, then on the boundary of the cylinder.
On the cylinder?
Yes, sir.
How do you get a curve which goes from the outside to the inside?
From passing through its boundary, like in
Over here?
Yes, sir. So at that point, it will not be differentiable.
Yeah, okay. So technically what we're assuming when we assume the cylinder is this is an open interval. Okay, so you can't really cross smoothly till there, because in this vertical direction, it has to be an open interval for a manifold, right? So, or it's a manifold with a boundary. So if you like, you imagine this to be infinite dimensional in the vertical direction. Or it maps to like some open interval 0, 1.
Yes. 0, 1.
Yeah, some open interval, okay, from A to B. Okay, so that you can't really reach the limiting point.
Yes, sir.
Okay, so sorry, let me just go back. So now what we want to do is on this n-dimensional orientable manifold, we defined an n form which is non-vanishing anywhere. This will be our integration measure. So now we can have multiple integration measures. Okay, so we say that there are 2 volume elements, omega and omega prime. These are any n forms, okay, which are non-zero over the entire manifold. We say that they are equivalent integration measures, not equal, but equivalent integration measures if there exists a strictly positive function h belonging to smooth functions on M, such that one n form is equal to this smooth function times the other, okay, other n form. Then these two integration measures are equivalent. They're not equal, but they're equivalent. Okay, that is, they define the same orientation on the manifold if h is positive. If h is strictly positive over the entire manifold, then these two define the same orientation of integration over the manifold. Versus a negative definite function. Okay, if 2 integration measures are related by a negative definite function, so that is, imagine instead of h, it's some g which is negative, okay, over the entire manifold. So then we would say that they define omega and omega prime define inequivalent representations, or they give an inequivalent orientations to the manifold. Okay, they give inequivalent orientations to the manifold. So any orientable manifold, there are only 2 possibilities, okay, of the inequivalent orientations. Okay, there are either the right-handed ones for which this Jacobian will be positive, or sorry, this function h, which relates everything within the same class, will be positive. And there's another class, okay, let me call this, things in the first class, and things in the second class are related by other positive functions to each other. But things between different classes, so if I take an omega 1 from the first class and omega 2 from the second class, these are related by a negative definite function. Okay, so I can have integration measures which are either right-handed, which are all related to each other by positive functions. Okay, or I can have integration measures which are left-handed, which are again related to each other by positive functions. But the relationship between any member of one class and a member of another class is a positive function. Is a negative definite function. Okay. So of course, what you call right-handed and left-handed is arbitrary. That's a matter of convention. Okay, that's a matter of convention. Okay, but once you fix one thing and call it right-handed, the other one automatically becomes left-handed. The other class is left-handed. Okay, so this is just like talking about the inside or outside of cylinder. Inside or vertical outside is a matter of convention. If I just give you a sheet of paper and I paint one side red and one side green, I could have equally well painted the other side green and the other side red. Okay, and there's no way to tell which one is better. Okay? Because also when I fold them together, okay, I could have folded like this, okay, in which case I have one orientation of inside and outside, or I fold it like this, in which case I would have a different color on the outside. Okay, so which one is inside, which one is outside, that's a matter of convention. Okay, the thing that will be true is that there will be two inequivalent classes. Okay, of n forms. So let's take a particular n form in some coordinate basis. Okay, so this is in some coordinate patch, okay, on the manifold. So we take some coordinate patch u. And on this coordinate patch, we have coordinates x, which means we have a basis of differential forms. So this is a basis of one forms. And now if we want a basis of n forms, it will just be dx1 wedge dot 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 wedge dxn. Okay, this is the basis of n forms. And this can be multiplied by an arbitrary scalar function. Okay, and this gives me the most general n form, okay, on this coordinate patch. This is the most general n form on this coordinate patch. So where HP is some positive definite function, we can choose it to be positive definite. Okay, on this chart U phi, okay, whose coordinate chart is x. Okay, so this is just what I said. Okay, more formally. So we have a function phi which maps us from this coordinate patch or this chart to coordinates x. Okay, where x is phi. Now, what we're basically going to show is that if we take this omega, okay, this omega can be extended over the entire manifold in such a way that this prefactor HP will be greater than 0 on any chart UI. Okay, and if M is orientable, okay, this omega will be a volume element that satisfies our conjecture that it's non-zero everywhere. Okay, because if on every chart you find that this prefactor, so basically if I have a different coordinate patch, I'll have different coordinates y1 through yn. And the claim is now if I have this omega, okay, now omega is not just defined in one patch, but it's defined over the entire manifold. And the claim is that if I can show in this patch that there's some h prime p, okay, this is not a derivative, it's just a different function. Okay, and this is also positive. So that basically I can go on defining omega patchwise over all patches on the manifold. And everywhere on the manifold, I can find positive functions like this. Okay, strictly positive, that is they're not zero anywhere. That means that the entire form omega itself, okay, this entire n form is non-zero everywhere on the manifold. And we'll show that basically on an orientable manifold, you can always find such an omega. And therefore, it will be a volume element that satisfies our conjecture. Okay, that there is a non-zero n form somewhere in the manifold. Okay, so the first thing that we'll do is we'll show that the positivity of this H, okay, the positivity of H, okay, this is actually going to be independent of any choice of coordinate system. Okay, so for example, suppose we look at the intersection region of, sorry, on just on this patch itself. Suppose we switch coordinates from x to y. Yeah, on this patch we switch coordinates from x to y. So now, so we have dx1 wedge dot 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 wedge dxn, and now we can make a coordinate transformation of this x1 through xn, and we can re-express them using these partial derivatives, partial x1, partial y mu1, dy mu1, wedge dot 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 wedge d partial xn, partial y mu n, dy mu n. So this is a summation. Mu1 is a dummy index which I'm summing over. Mu n is also a dummy index which I'm summing over. Now these are prefactors. Okay, these partial xn, these are prefactors. Here the x1 is fixed, here xn is fixed. Okay, the n index is fixed. What I can do is I can move these prefactors out in front. Okay, so I can write the prefactors as this: partial x1, partial y mu1, dot 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 partial xn partial y mu n times now this dy mu1 wedge dot 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 dy mu n. Okay, so this is just the same thing re-expressed in a different coordinate system with different dual basis vectors. Okay, or a different basis for the n forms. And now, if you remember what I had mentioned in an earlier class, I can now think about anti-symmetrizing over these n forms, okay, over these, or I can imagine anti-symmetrizing over the coefficients. So I'll do exactly that. Okay, so I'll write this now as fixed dy1 wedge dot 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 wedge dyn, but now I'll anti-symmetrize over the coefficients. Okay, dy1 through dyn. And so now this entire thing, okay, can now be written as the determinant. Okay, since this is an anti-symmetrization, that means that I will have terms like partial x1, partial y1. Okay, and every time I differentiate, I always have a different derivative with respect to a different y. Okay, so this is a sum over many terms. Okay, and every time I'm differentiating with respect to a different y. So it's really like taking the determinant of this matrix: partial x1, partial y2, partial x1, partial y3, dot dot dot, partial x1, partial x2, partial y1, partial x2, partial y2, partial x3, partial y3. Okay, so if I want to take the determinant of this matrix, what I will do is I will pick out any element, okay, of one row, another element from another row, and so on, another element from another row, and I will assign an appropriate sign to them based on which elements I'm picking out. That assignment of signs is based on the permutation, okay, associated with if I pick out from 1 through n, okay, if I pick out this entry from the first row, this entry from the second row, and so on, okay, depending on what entries I'm picking out, it corresponds to a particular permutation of the numbers 1 through n. And this anti-symmetrization basically has the sign associated with that permutation, which is what you have when you expand out the determinant. Okay, so what you will get is h of p times this determinant, okay, of partial x mu partial y alpha, dy1 wedge dot 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 wedge dyn. So this is h of p times the Jacobian times dy1 wedge dot 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 dy. Okay. So now, okay, if you have so if I have this a different coordinate patch, okay, so imagine that this is u1, this is u2, this has coordinates x, okay, and this has coordinates y, and in the overlap region, both x and y are valid coordinates. Okay. Now in the overlap region, what this is telling me is then now if I had a form which I had written like this, okay, in the u1 coordinate system in this overlap region, then the same form can be re-expressed in this way, okay, using the coordinates of u2. Okay, it can be expressed as h of p times j dy1 wedge dot 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 wedge dyn. Now, if m is orientable, if m is orientable, by definition, what we mean is that we can always find a coordinate system, given a coordinate system x, we can always find a coordinate system y on this other patch u2, such that in the overlap region, the Jacobian is positive. Okay, that's a definition of what we mean by orientability. So if it is true that we can find the coordinates y such that the Jacobian is positive, then that means that we have now expressed, okay, using some other function h prime p. Okay, we now have a strictly positive function times dy1 wedge dot 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 wedge dyn. Okay, so now we've expressed the same omega in this overlap region using some positive function times dy1 wedge dot 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 wedge dyn. Okay, and this can always be done in any overlapping region on an orientable manifold. So now, so this quantity h prime p is also positive, okay, because it's h of p times the Jacobian. Okay, and the Jacobian can be chosen to be positive by choosing this coordinate system in an appropriate way, and this choice can always be made on an orientable manifold. Okay, so now the point is that we can now start assuming that we have an omega, okay, which is defined in this way, where we choose a non-zero function, dx1 wedge dot 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 wedge dxn. Then now we can go into the overlap region and then write it using the coefficient h prime p. Then from the overlap region, we can extend this now to the rest of u of j. Okay, and we can choose the coefficient to be some positive function in this patch. And by doing this, you can go on hopping between coordinate patches and go on extending your omega over the entire space. Okay, and you can always do it in such a way that in every region, it's expressed as some function, and you can choose your coordinate systems in every patch such that it can always be written like this in every patch. Okay, where this function is strictly positive. Okay, so basically now that you have a strictly positive function, omega in particular, this omega vanishes nowhere since h of p is non-zero everywhere, and it's smooth, okay, over the entire manifold. So therefore you have constructed an omega. Okay, it is always possible. You've shown that it is always possible to construct an omega which is non-zero everywhere on the manifold. Okay, and this omega is a rank, belongs to the space of n forms. Okay, so this is a volume element, okay, which we can use to define integration. Okay, and we'll do that next. So just to give you an idea of how this would fail, okay, so on the Mobius strip, if I define, for example, so this was coordinate patch u1, and if I define dx wedge dy, okay, as in one patch, I can define this. Okay, I can define it like this. And here is the overlap region A, and here's the overlap region B, and here's the other coordinate patch with A prime and B prime. Okay, so now in my overlapping patch, okay, so in A and A prime, okay, on A prime also I would have, so for example, sorry, to be more clear, this would be dx1 wedge dx2. This is x1, this is x2, and this is y1, this is y2. Okay. So now in the overlapping patch, what I would find is there's a smooth mapping from this omega to omega defined in this patch, which I can write as dy1 wedge dy2. Okay, and this fixes, and I fixed my y1 and y2 coordinates. Okay, but now what I would find is in the overlap region of B prime, okay, I can no longer define my omega this way. My omega in the region B prime would then therefore necessarily be of the form, if I want to smoothly match it into this omega here, it would be minus of dy1 wedge dy2. Okay, so basically I cannot choose it to have a strictly positive coefficient. If I choose it to have a positive coefficient in this region, okay, it will have a negative coefficient in this region. Okay, and therefore, okay, so omega will be something like minus dx wedge dy. So therefore, I cannot define a volume form, okay, which is non-zero everywhere. Okay, somewhere, if I want omega to smoothly vary, then somewhere it has to transition from having a positive coefficient to a negative coefficient, which means that somewhere it has to go through zero. Okay, and the only way that can happen is if I choose it to be zero somewhere. Okay, and basically, if I have an n form which is zero at some points on the manifold, I cannot use that to define a volume form. Okay, so basically this is omega in this entire coordinate patch. Okay, and sorry, in this entire coordinate patch U2. And in the region of A prime, omega looks like this. In the region of B prime, omega looks like this. But omega must be defined over the entire coordinate patch. So somewhere in between, it has to transition from the coefficient being positive to the coefficient becoming negative. So somewhere it should go through zero. Is that idea clear?
Sir, why omega should be minus dy1 wedge product dy2 for B prime region?
Okay. So we've seen that so x1 and x2, right, were related by this quantity, right? Something like this, right? I'm going to ignore again the y1, y2 plus some constant, right? This was the coordinate transformation in the region of B and B prime. right?
Yes.
So now what I want to do is calculate dy1, dy2. Okay, and that will be exactly the same determinant. Okay, I mean, you can show this in multiple ways, but let's just argue like this. Okay, so this is what you would have. Okay. So now it's obvious, right? So dx1 wedge dx2 is just directly equal to minus dy1 wedge dy2. I mean, what you can actually do here is dy1 is equal to partial y1 partial x1 dx1 using the tensor transformation rule, right? And that's but it's effectively just going to be this matrix again, which was
Yes, sir. And for A prime, the matrix is identity, so it is dy1 tensor product. Sorry,
yeah.
wedge product.
Yeah, that's right.
Okay.
Okay, so once I fix the coordinate system on y1 and y2, and once I demand that I give you the mapping between a and a prime and b prime, then it automatically fixes the omega defined here as dy1 wedge dy2, which is the same as dx1 wedge dx2 in the overlap region. And here in the overlap region, okay, I will first of all get omegas minus dy1 wedge dy2. Okay, I will get omegas minus dy1 wedge dy2, and which is exactly the same as dx1 wedge dx2 in the overlap region. Okay, but now the problem is that on this patch, okay, the omega must transition from dy1 wedge dy2 to minus dy1 wedge dy2, which means it has to go through 0 somewhere. If omega is smooth, and that's exactly why you will not be able to define a volume form on the Mobius strip. Okay, it's the same thing as saying when I glue together the sides, when one side is red and one side is green, somewhere I transition from red to green. Okay, if I want that transition to be smooth, then the red to green must go through some intermediate shade. Okay, which roughly if red is +1 and green is -1, then I must go through 0 at some point. Okay, that's really the same thing now said using the language of differential forms. Is this fine?
Yes.
Okay, so now what we're going to do is finally we'll define now that we have a notion of what we mean by a volume element. You can have positive volume elements or you can have negative volume elements. That is, you can have, sorry, not positive or negative. You can have left-handed or right-handed volume elements. Okay, it's arbitrary which ones you call right-handed, which ones you call left-handed. But once you define them on an orientable manifold, there are only these two classes. So, these are volume elements which are non-zero everywhere. Okay, now you can define the integration of a function. So now if I have a function which is from a manifold M to real numbers over an orientable manifold M, okay, we can define the integration using a differential form omega, okay, and n of rank n. Okay, so the strategy will be as follows. First, we'll define the integration over a particular coordinate patch. Okay, we'll define the integration first over particular coordinate patch. So in this particular coordinate patch, we'll define the integration of the function f. Okay, by an mn form. Okay, f omega. Okay, so the rank of the form has to be the same as the dimension of the manifold. So f omega integrated over this patch, okay, will be equal to f, okay, at phi I inverse of x. So which means the points on this manifold P, okay, will be phi I will take me to the map phi I takes me to its coordinates. So given in X, I invert it. I use the inverse map to locate the point on the manifold. And from that point on the manifold, I now get f of, what is the real number associated with that point? That is f of p. Okay. And now what we do is we take f of phi I inverse x, okay, which is the same as taking f of p. And we now multiply by omega, and omega, we assume this n form can be written in this coordinate patch as some function h of x, okay, or if I want to be very precise, h of phi I inverse x. Okay, which means, I mean, I could have written this as f of x also in shorthand, and this is h of x, okay. We understand why we inserted this phi, okay, because strictly speaking, the function is of points on the manifold, not of coordinates. Okay, so there's one extra step to get from coordinates back to the point of the manifold, and from point of the manifold to its image under this function f. Okay, so now we assume that omega can be written in the form of h dx1 wedge dot 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 wedge dxn. And we define the integration now. We define the integration to be in this coordinate patch. Okay, we will use f times h, but then we'll just do a normal integration over coordinates dx1, dx2, dot 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 wedge dx. Okay, so this will be an ordinary integration of n variables. Okay, now the key point is, okay, we want the integral to still be coordinate system independent. Okay, so the question is, if we define the integration this way, okay, so what is the extra thing that we've got? We've got this factor of h over here, which came from the integration measure. Okay, so if we define the integration this way, does this factor of h change things in such a way that now this definition becomes coordinate system independent? Okay, that's the first question that we want to ask. And the answer is surprisingly yes. Okay. What happens to omega under a change of coordinates? Well, omega we've seen is h of p times dx1 wedge dot 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 wedge dxn. This becomes, under a change of coordinates, it's h of p times this determinant partial x mu partial y nu partial y1 wedge partial yn. So if we use this definition, integral f omega under a change of coordinates, okay, should just become, this is now the new h of p. Okay, so this is h prime of p. So it's h times this determinant, okay, which is h prime, times an integration dy1 dot 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 dyn. Okay, and if we use the y coordinate system, then our definition tells us this is the integration we need to do. If we use the x coordinate system, then we get that this is the integration that we need to do. Okay, but the key point is that because of the positivity of the Jacobian, okay, if we choose our coordinate system such that the Jacobian is always positive, okay, then these two integrals are actually the same. Okay, because now I can think of this h as, instead of this determinant, as instead of being associated with this prefactor, is now associated with this dy1 wedge dyn. dy1 dot 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 dyn, this integration. And this is exactly when I change the integration measure, it's now dx, to a change of variables, it's dx1 dot 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 dxn. Okay, the key point is about the orientation of the integration. Normally, when you think about the orientation of the integration, okay, we use the mod of, so when we change variables, we get determinant of the Jacobian, mod of determinant of Jacobian times dy1 dot 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 dyn. The key point is that here we're not getting the mod of the Jacobian. We just get the determinant of partial x mu, partial y nu. Okay, but because we can choose our coordinate systems in such a way that we always have positive we choose our coordinate system so that we have a positive j. Okay, and then this integration, okay, is basically defined, okay, with one choice of orientation. Okay, this integration agrees. Okay, both these integrations agree. Okay, as long as we define them with the same sense of orientation. That is, we always choose our coordinates such that when I transform from one coordinate system to another, the sign of the Jacobian is always positive. Okay, that's a choice that we make. Okay, of the kind of coordinate systems. Are we doing a left-handed integration or a right-handed integration? We choose to always do one. Okay, and when we switch from one coordinate system to another, these two are exactly the same. Okay, So because of the positivity of j, this integral is the same in all right-handed coordinate systems. In all right-handed coordinate systems, you will get the same result for the integration. If I switch to a left-handed coordinate system, I would get an extra minus sign. Okay, so it's like doing an integration over dx dy, okay, with a positive orientation for the area element versus a negative orientation for the area element. Okay, I will only get one or the other. Okay, but once I fix the orientation, any change of coordinates, as long as I make the change of coordinates in such a way that I preserve the orientation, okay, then I will always get the same result for the integration. Is this clear?
Sure. How did we get from the wedge products of dx1 to dxn to the products of dx1, dx2, and dxn?
This is the
Where did
definition. So this
No.
definition seems like it's a coordinate system dependent definition. Okay, so I define the integration of f with this measure omega in a coordinate patch ui. I give the definition using one coordinate system. Okay, I say that it's equal to f of phi I inverse x, h of phi I inverse x, dx1, dx2, dxn. Right, this is a definition given to you in one coordinate system. What we have shown is that no matter which coordinate system you choose, if I'd chosen the y coordinate system, I would have gotten this integration. If I'd chosen the x coordinate system, I would have gotten this integration. As long as these two coordinate systems have the same orientation, the result of this integration, whether you got this or this, would be the same. Okay. Therefore, this definition, although it appears to be a coordinate but specific to a particular coordinate system, is actually coordinate system independent.
No, I'm trying to ask whether omega was h of p and dx1 wedge product, dx2 wedge product until dxn. How did we get from that to without the wedge products? The simple
Again,
ordinary
I
integration.
defined it this way.
Okay. This is the definition.
This is a definition that I give to what I mean by this integration.
Okay.
Okay, and the important point is that you would like this definition to not depend on the coordinate system, because f is not a coordinate, doesn't depend on any coordinates that I choose. Omega doesn't depend on any coordinates that I choose. Okay, it's an n form. The point is that I define it and it looks like the definition is coordinate system dependent. But what we find is that whether I calculate this in some y coordinate system or x coordinate system, as long as those two coordinate systems have the same orientation, I will get exactly the same result for the integration. Therefore, even though I defined it in a way that looks like it's coordinate system dependent, the result of this integration is actually coordinate system independent.
Okay.
Yeah, that's a key point. Okay, yeah, here dx1 is a one form. Here this dx1 is just a normal measure of Riemannian integration. Okay, so now what we've done is we've defined integration in a patch. Okay, we've defined integration in a patch. So our strategy now is, now that we've defined the integration over a patch, we want to define the integration over the whole manifold by adding up the integrals with the same orientation in all the patches. That is, now we have this patch, other patches, and we want to define the integration over this, plus the integration over this, plus the integration over this, but we want to integrate them with the same orientation. Okay. So the orientability of M will be useful. The fact that all of these patches you can choose coordinate systems on all the patches such that they all have the same orientation, that will be important. Okay, so that's why you need the entire manifold to be orientable. The second thing is the overlap regions, okay, between the patches, we don't want to double count the integration, right? So how do we take care of these overlap regions? How do we deal with the overlap regions? But basically now what we have is we have an integral over f omega, okay, and defined over one patch. What we want to do is sum this over all the patches, okay, and then we don't want to double count in the overlap regions. Okay, that's the key idea. Okay, and all these integrations, the point is that we could define this integration in two different ways. Okay, we could choose either orientation. We want to choose them always to be in one orientation. So in every patch, we want to choose, let's say, a right-handed orientation, so that the integration here is a right-handed orientation, right-handed orientation, right-handed orientation. Okay. Okay, so so the key thing is to deal with these overlap regions. Okay, we will take an open covering of M. Okay, so that is a covering that of all of these. I mean, a set of open sets that covers the entire manifold M, such that each point P belonging to the manifold is covered only by a finite number of UI. So if I have one point P, I'm choosing the set of UIs such that the point P can only lies in the intersection of a finite number of the UIs, not in an infinite number of them. Okay, so this is not, it's not always necessary that on every manifold you can do this. Okay, there are some manifolds on which some points might lie in can only lie in an infinite intersection. Okay, that is I have to define an infinite number of intersections, okay, of many points, and this point will lie in that manifold. It's not possible to subselect. Okay, if I want to cover the whole manifold, it's not possible to make a subselection of these coordinate patches UI or these open sets UI. So, but these spaces are rather pathological. They're not the typical spaces that you think of are not like this. You can always cover them with a finite number of open sets, so such that any point P lies in a finite number of open sets. But if you want to look up some examples of this, one prototypical example, which I won't discuss, is something called the long line. Okay, where every point belongs to an infinite intersection of many open sets. Okay, and you cannot go to a finite number of open sets. Okay, so we'll make that assumption. Okay, and this additional, when you make this assumption, you are actually restricting to a subset of manifolds called para-compact manifolds. Okay, it's just a fancy way of saying that we'll assume this property. Okay, that is every point P only lies in a finite intersection. So let's say there are only 3 coordinate patches in which this point lies. Okay, so now what we'll do is, if a family of differentiable functions epsilon I of P satisfies this property, okay, that is, so now imagine that I have a point P and it lies in the overlap between U1, U2, U3, U4 till some UM. M is finite, okay? And now I will assume that associated with this point P, okay, I can define some functions epsilon I of P such that I am going to weight the integration in this overlap region by, so epsilon 1 of P, which is associated with this U1, epsilon 2 of P, which is associated with U2, epsilon 3 of P, which is associated with U3, and so on. Okay, in such a way that epsilon I of P, so this epsilon I of P is defined such that, first of all, this function is differentiable. Secondly, it lies only between 0 and 1. Okay, so these functions lie only between 0 and 1, including 0 and 1. Epsilon is 0 if the point P does not belong to any of those UIs. Okay, so for example, there could be other patches on the manifold that don't contain this point P. In that case, epsilon associated with this patch, okay, is 0. And secondly, all these epsilons, okay, if I take the patches, including the ones which doesn't lie in, so if I sum over all coordinate patches that cover the entire manifold, so now imagine that I have this manifold and it's covered by all these coordinate patches. Okay, and sorry, let the total number of patches on the manifold be small m. Okay, then there's epsilon 1 of P plus epsilon 2 of P plus dot 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 plus epsilon m of P. Okay, if I take for every open set, okay, or every coordinate patch, there is an epsilon that I can define associated with that point, such that this is equal to 1. Okay, then if I can define, so this sum is equal to 1 for any point P on the manifold. Okay, so for any point P, there exist these functions such that the sum is equal to 1. Okay, and then this family of epsilon I of P, these functions epsilon I of P, which are associated with every patch. Okay, so associated with this point P, there are some of these will be non-zero. Okay, some of them will be 0. Some of them will be 0 because the point P doesn't lie in those patches. Okay, but the other ones will add up to 1. Okay, this epsilons of P's will add up to 1. So this is called a partition of unity. Okay, I'm basically subdividing 1 into some numbers, okay, which lie between 0 and 1. And it's called a partition of unity subordinate to the covering UI. So this is associated with a point P and all the open sets UI on the manifold. Okay, so given a point P and the UIs, okay, every point P has some weight, okay, some weight associated with every UI. Okay, and now what we can do is we can define f of P. Okay, this function f of P by definition, okay, can be written as f of P times the summation of, so any function on the manifold now can be written as f of P times this summation over epsilon I of P, because all the epsilon i's associated with that point P add up to 1. Okay, so this is by definition 1. And now this does not depend on which coordinate patch we choose. Okay, the value of the function. So if I have some function from the manifold to real numbers, okay, this value of this function at the point P doesn't care about any partitioning that I do. So I can pull it inside the integration. Okay, so the idea is something like this. So here's a point P, okay, and it lies inside the patches U1, U2, U3. I associate a weight F1 of P associated with U1, F2 of P associated with U2, F3 of P associated with U3. What are these F1, F2, F3? It's f of P times this epsilon I. Okay, so what I have done is, although this point has mapped to f of P, what I do is I break up f of P into 3 parts, f1 of P, f2 of P, f3 of P. Okay, in such a way that all of these added up together give me the full f of P. But this f1, f2, f3, okay, basically tell me about the, roughly speaking, it's a way of splitting up the f of P into a part which is associated with this coordinate patch, a part which is associated with this coordinate patch, and a part which is associated with this coordinate patch. So this is the way I'm going to take care of the overlaps. Okay, is I'm going to break up f of P into parts which I can associate with different coordinate patches. Okay, so because of the para-compactness property, there's only a finite number of these f of P's, okay, that I'm splitting into. Okay, so this is called the partitioning. Because of the partitioning of unity, we're always able to do this. Okay, so now what we can do is we can now define, okay, the integration of f omega over the entire manifold. Okay, we can do the integration by summing over all the coordinate patches. Okay, but instead of integrating f itself, okay, we integrate fi. Okay, that is associated with each coordinate patch. We don't integrate the full function, but only the function that we've associated with that particular coordinate patch. Okay, fi of omega. Okay, so we had defined how to do the integration over a coordinate patch earlier, and now we do the integration over the full manifold. Okay, so the only tricky thing was, in order to do the integration in the overlaps, okay, we decided how much weight to give coordinate patch U1, how much weight to give coordinate patch U2, how much weight to give coordinate patch U3. And then in the overlap region, we basically assigned that weight F1, F2, F3. Okay, sorry, epsilon 1, epsilon 2, epsilon 3. Okay, and we multiplied by the function by this. Okay, and epsilon 1, epsilon 2, epsilon 3 add up to 1. So we call this F1, F2, F3. And in coordinate patch U1, we only integrate over F1. Okay, in coordinate patch F2, we only integrate over U2. Sorry, in the coordinate patch U2, we only integrate over F2. And the coordinate patch U3, we integrate over F2. Okay, and this epsilon is these epsilons are defined pointwise. Okay, So that means these points F1, okay, are defined sort of pointwise. Okay, so finally what you get is a definition of this integration. Okay, so now I split the integration over the manifold into, using this partition of unity, I've split it into an integration over patches. Okay, each point lies in a finite number of patches by the assumption of paracompactness. And now I do the integration over patches, but I don't integrate the full F, I integrate the F which is weighted by these epsilon i's. Okay. And this definition is now independent of any choice of this open covering UI. Okay, it doesn't really care about what particular choice I made of these patches. And it's also independent of any coordinate systems that we choose. Okay, and it's also independent of how we choose to make this splitting into epsilon1, epsilon2, and epsilon3, how we partition, how we do this partitioning of unity. Okay, so this gives us a definition for what we mean by an integration over the manifold. Is this idea clear?
So one thing, like this box equation, the way like so integral over mf omega, like we've seen that we can write f as sum over I fi. Yeah, and so this is okay, like f I can replace by sum over I fi, and omega is there, and this integral over m I can also write it as like sum over I is already there, so sum over I integral over ui. So is that correct?
Yeah,
I mean,
so in another way of saying it is, I mean, I have to give a definition to what I mean by integration over manifold.
yeah.
Okay, so it's not that I'm splitting this into, I mean, you can think of this as, okay, I'm splitting this and writing it as summation over fi times omega. That's actually not right. No. So f at every point on the manifold can be split, right, into summation over fi. That is correct.
Yes, sir.
But
This is
but this splitting depends on which coordinate patch you're in.
yes.
Okay,
So
so you can't do this splitting in over here. Okay, but you can define it here when I define a sum over coordinate patches.
yeah, so this is again just like a definition.
It's a definition. It's a definition.
Yeah, so one thing like that like that partition of unity thing is that I understood, like to treat f just to write that as sum over IFI. But how do we get rid of that double counting by this?
Because now, for example, when so epsilon1, epsilon2, epsilon3 are appear only their sum is 1, right? So now if I take a point P in the overlap, okay, this sum will give me epsilon1 times f omega in, from the patch U1 plus epsilon2 from, I mean, epsilon1 depends on P. Okay, so maybe it's better to keep it inside the integral. So what I'll have is summation over I integral over ui fi omega, which is summation over I over ui epsilon I times f omega. Okay, so now what I'm doing is basically I've partitioned in such a way. The partitioning is changing from point to point, but the point is that at every point, the epsilon i's all add up to 1. Okay, which means that if I have done the integration this way, okay, roughly speaking, if you assume everything is smooth, then you can imagine that that for every point now, okay, I'm not assigning it the full weight, right? I mean, so I'm not assigning it the full weight of f. I'm only assigning it a partial weight of f. So that basically when I add up all the patches, it's only then that I get the full weight of f associated with that point. So this summation and this epsilon together, right, are giving me the full weight of f associated with that point. Okay, if you like, okay, if I imagine that epsilon was independent of which point I took, then I could pull this epsilon outside. Okay, and roughly speaking, this is what you're doing, right?
Yes, sir.
Okay, and basically what you're saying is now that with each integral is weighted by this epsilon.
Yes, like only if like we have a point B which is only inside one U, then only it is one, and for rest it is zero. So this holds. And if let's say there are two U's which cover with some half factor, then also this holds. So
Yeah, right. Okay, it may not be half, and it may also vary from point to point in the overlap. Okay, that's also the key point. That this epsilon of p may, but the point is it doesn't depend on what particular choice I make for this function. The result of the integration, it doesn't matter. I mean, I can treat the overlaps in many different ways. I can, assign 3/4 weight to one and 1/4 weight, or I can assign it in a, non-uniform way. It doesn't matter what way I choose. This definition, even though we define it this way for a particular partitioning, the result will be independent of how I choose to partition unity. Okay, and it'll also be independent of how I choose my coordinate patches on the manifold. To calculate it, I might choose a particular coordinate patch, and to calculate, I might use a particular partitioning of unity, but the result of the integration will not depend on those choices. Okay, I'm not proving it, but it's intuitively obvious why that should be true, right?
yes, sir, it's just like using coordinates, but the final answer is same. So here also like.
Yeah. Okay. Okay, so let me just do one last thing. Okay. So now the thing is there are many possible volume forms that you can do to do integration. So the thing is, what is the natural choice for this volume form? Okay, because let's say all the right-handed volume forms, any of them you can use to do this integration. Okay, so if I have a function f, I can choose any right-handed volume form and let's say do an integration. If I choose a left-handed volume form, then I would get a different sign for the overall integration. Now the point is that which one should I choose? There are many possible omegas, even if I work with the right-handed one. So you might expect a natural choice is, why don't I choose this h of p? Why don't I choose it to be 1? Okay, then my integration is just f times dx1 dxn, right? Why do I worry about this h at all? But this depends on the coordinates that we use. In one coordinate system, it might be 1, but in another coordinate system, this coefficient will not be 1. Okay, so choosing it to be 1 doesn't really make sense. Okay, it's I mean, there's no preference for choosing it to be 1. That in a particular coordinate system, you can choose it to be 1, and that's a perfectly valid choice, but it may not be valid in general. And also on a general manifold, okay, this is only defined in a particular coordinate patch, right? How do you define across coordinate patches? Okay, so on a general manifold, there are many possible choices of this omega n that you can choose to do the integration. Okay, that is the first thing. So there's no preferred choice as long as you choose something in the right-handed, among the right-handed n forms. Okay, you can always do an integration and you will always get the same sign for the result of your integration. Okay, not the same sign. Okay, it depends on if f is positive, you'll always get the same sign. Okay, if f is for any other function, it's like it defines an orientation to your integration. However, if your manifold M now has a metric on it, like in GR, which we're interested in, then there's a preferred choice, okay, of what this integration measure should be, okay, or this volume element should be, and that is an M form, omega M, which is the square root of the mod determinant of G, where this is the determinant of the metric, times dx1 wedge dot 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 wedge dxn. Again, so this is in section 7.9 of Nakahara. So I'm jumping from chapter 5 to chapter 7 now. But again, this looks like it's a coordinate system dependent definition. But actually, this is a coordinate system independent definition. Okay, it turns out to be coordinate system independent. Okay, so this is a natural choice given a metric. So you're given a particular 0-2 form. So using this 0-2 form, it turns out that there's a particular n form that you can define on the manifold, which is this one. And this one turns out to be coordinate system independent. And this is therefore becomes, given a metric on the manifold, this is now a preferred integration measure. Okay, so this is called an invariant volume element. So if we, so now what you can do is, so the first thing we'll show is that this definition is actually independent of the coordinate system that we choose. So let's suppose that we chose a different coordinate patch y, okay, or coordinate system y on the same patch. So we would have dy1 wedge dot 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 wedge dyn. And with this definition, we would have determinant of g prime, where g prime is the metric expressed as g mu nu dy mu dy nu. Okay, so this is the determinant of this, these metric coefficients expressed in this new basis. So I can express the metric coefficients in the new basis, okay, that is in the y basis. I can express them in the x basis, so I can write them as partial x alpha, partial y mu, partial x beta, partial y nu times g alpha beta. This is just the tensor transformation, okay, for a 0-2 tensor. And now if you look at this, this is like Jacobian transpose times G times Jacobian in matrix notation. It's the determinant of Jacobian transpose G Jacobian, which is equal to, okay, so the product of determinant of, product of matrices is equal to the determinant, the product of the determinants, okay? So it's equal to determinant of J transpose times determinant of J times determinant of G under the square root. And the product determinant J transpose times determinant of J, okay, is just determinant of J square, determinant of J whole square. And so if I take the square root, I get mod of determinant of J, okay, times under root mod determinant of G, okay, by this mod sign. And so what I get is now, okay, I can also write this as mod of determinant of partial x alpha, partial y mu, and times so let me just recap. Okay, so I have mod of determinant of J times mod of determinant of G. So that's this factor. Okay, mod determinant of J times square root of determinant of G. Now I re-express this partial y1 wedge dot 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 wedge partial yn using the x1 through xn. In this case, I will get the determinant without the mod. Okay, determinant of partial y alpha, partial x mu. So this is the inverse Jacobian and this is the Jacobian. Okay, or whichever way you like. And now these two factors exactly cancel out if x and y are coordinate systems with the same orientation. If x, y have the same orientation, okay, then what I will get is exactly square root of determinant of G. So this Jacobian will have the same sign. So if it has a positive orientation, okay, so if the Jacobian is positive, x and y have the same orientation. So these two factors will cancel out. Okay, and I'll just get square root of determinant of G, where this G is now expressed, is the metric coefficients expressed in the x basis. Okay, times dx1 wedge dot 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 wedge dxn. So whether I use the rule in the y basis, okay, the rule that I defined above in the y basis, or whether I use the rule defined in the x basis, I would have got the same result. That's why this definition of this n form, okay, is actually independent of my coordinate system. It's a preferred n form or a volume integration, okay, on a manifold, on an orientable manifold. Okay, so any scalar function on M can now be integrated using this volume form. Okay, so you can write something like an integration over the manifold f times square root of the determinant of G times dx1, dx2 wedge dxn. Okay, and what I would do is, again, if I want to define this integration over many coordinate patches, I do a partition of unity. Okay, and I write this as summation over fi, integration over coordinate patches, and sum over I, where I is the sum over coordinate patches. Okay, dx1 to dxn. So this defines how I do the integration over a manifold. Okay, when I have a metric. The two conditions to do this integration, for this integration to be well defined, is that the manifold must be orientable and it must be paracompact. Okay. So you might have seen things like, when I define the action in general relativity, it'll turn out that we'll define the action you might have seen in various textbooks. It might be of this form, times a Lagrangian. Okay, this is the measure of integration, and now you understand why this is the correct measure. The sensible way to define integration is using forms. There is a preferred form which we use to do the integration. Assuming that there is a single coordinate patch that covers the entire manifold, you can do the integration this way. Okay, you can do the integration this way. If you don't have a single coordinate patch that covers the entire manifold, you have to do the partitioning of unity and write the integration like this. Okay, like this. Okay, and then you have this Lagrangian over here. Where sometimes small g is used for mod determinant of g. Okay. Any questions here?
Sir, just one thing, like when you said that those two determinant will actually cancel out, like j and 1 by j, like if I define it that way, like if like as a manifold is orientable, that's why this determinant of j is positive. So we can write j mod j as j. So j and 1 by j will cancel out.
No. What I was saying is that in any particular coordinate patch. Okay, so I'm not even changing coordinate patches. I'm just in one coordinate patch, u. But what I'm claiming is that this yeah. So firstly, within a coordinate patch, if I switch from one coordinate system x to another y, such that this form has the same orientation. Okay, that is the coordinate systems x, y have the same orientation. Then then the Jacobian will be positive. Okay, so within the coordinate patch, this definition is coordinate system independent. This you agree, right?
Yes, sir. Yes, sir.
And now between coordinate patches, okay, if the manifold is orientable, then I can always choose a coordinate system x on this and y on this, such that in the overlap region, okay, again, these definitions of omega m defined using this patch versus this patch, they would agree, because this definition is both coordinate system dependent as well as patch dependent, right? But on an orientable manifold, I can always choose it such that this definition is actually independent of which coordinate system I use and which patch I use.
Yes, sir. Yes, like in that, when one of the steps, like what I was saying, that like as it is orientable, so the determinant is positive, greater than 0. So that mod j we can replace by j, so that will cancel that inverse thing. Like if it was not orientable, then we would have had minus. Like if they
Yeah, but to be clear, in that case, you're talking about in the intersection region between the patches, and y is the coordinates of the second patch, and x
yes,
is the coordinates of the first patch. What I was talking about was within a single patch, if I change a different coordinate system, right? That is within x itself, if I change my coordinate system, then I would have still got the same answer if x and y were two coordinate systems on the same patch with the same orientation. But both these statements are true and are important to show that this omega m is both coordinate system independent and patch independent.
Sir, shouldn't this happen? Doesn't this happen always? Like there are some cases when this happens for like is it possible that these two statements don't like this always happens, right?
That it's coordinate system dependent and patch independent?
Yes, yes.
No, it would not be true. Supposing we found that, so what I did was I used the rule. I used this rule in coordinate patch y to write this. Okay. So using the coordinate system y, I use the rule that I have to take the determinant of g and dy1 wedge dot 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 wedge dy. Okay.
Yes,
That is just from the rule.
yeah, in the same patch, two different coordinates.
Two different coordinates. Okay.
Yeah.
And then I use a different rule to write this. Okay. But see, it's not guaranteed when I switch from one to another, right? If I have dx1 wedge dot 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 dxn, I mean, in general, when I switch coordinate systems, I will have a different function here, right? maybe not h, some f. Okay. Now the important point is, what is my rule for what is this function? My claim was that I will on a manifold with a metric, I use the square root of determinant of the metric coefficients expressed in the x basis. And my rule was that I will use the square root of determinant of the metric using the y basis. The fact that these two are equal under a coordinate transformation is not obvious at all, right? It just turns out to be true. Right? If I'd chosen a different function here, okay, so for example, supposing I just chosen determinant of g here instead of the square root of determinant of g, then this would not have been true. That the definition is coordinate system independent. Because now what would have happened is I would have got, okay, so if I use this definition, I would have got an extra factor of these Jacobians, right? So I would have determinant of g, but instead of the square roots, I would have an extra factor of the Jacobian. So I would have determinant of j square. Okay, and now if I use my transformation rule, I'll get a determinant of j. And so I'll have an extra factor of the Jacobian sticking around. Okay, even if, let's say, I choose positive orientability. And this may be coordinate, I mean, it may vary from point to point. So this is a new function on the manifold. So the fact that it's exactly the determinant of square root of determinant of g after the coordinate transformation, that is the remarkable thing, right?
Yes, sir. Yes, sir.
That's why you can't choose arbitrary measures on a metric on the manifold. There's a natural choice, which is square root of determinant of g. That's a specific choice. Okay. There's something more. Are you guys okay with another 10 minutes and I can just finish this thing? This is a slightly important topic.
Yes, sure.
Yes, sir.
Yes, sir.
Okay. So let's, so this is called Stokes theorem. Okay, so I'm just going to state some results without proof. Okay, so let M be an n-dimensional manifold with a boundary. So now this is so imagine like a cigar type shape. Okay, with a boundary now. This boundary is a circle. So S1 is the boundary of this manifold. Okay, so the cigar is the manifold, this circle is the boundary. So till now we've not defined manifolds with boundaries, right? We always work with open sets so that the boundary is not, part of the manifold, but now we define a manifold with the boundary. This partial M is the boundary manifold. So now Stokes theorem is the statement that if I have an n-1 form on this manifold, so not an n form, which is a volume element, but an n-1 form, then the claim is now I do an integration of d omega. So d omega is an n form. Okay, omega is an n-1 form. So d omega is an n form. So I do the integration of d omega over the manifold. Okay, this integration is defined. Okay, I'll assume it's an orientable manifold. Okay, then the claim is that this result of this integration is equal to omega integrated over the boundary manifold. Okay, because omega is an n-1 form. So now, of course, omega is defined over the entire manifold M, but I can take omega on this boundary manifold. Okay, so that's omega n-1 just projected on the boundary itself, like whatever the values are on the boundary. And I can integrate just over the boundary. Okay, and that gives me the integral of partial M of omega. I'm not proving this, but this is Stokes theorem. Okay, I won't discuss the proof here, but I'll state the results. Okay, so the important thing about the Stokes theorem is that it's actually a unified treatment of Gauss's law and what you think of as Stokes theorem. Okay, in 3 dimensions. So let's see how that's true. Okay, so this is a very nice and compact way of writing both Gauss's law and Stokes theorem are actually encompassed over here. So let's do first Gauss's law. Okay, so Gauss's law is we take a solid ball in 3 dimensions like this. This is our manifold M. The boundary of this ball is S2. Okay, it's this 2 sphere, which is this boundary. So partial M is S2, M is this ball B3. Now omega is a 2 form. Okay, which is so we have a 3-dimensional manifold. So we take a 1-dimensionless form. So we take a 2 form. So omega can be written as 1 over 2 factorial omega xy dx wedge dy, omega yz dy wedge dz, omega zx dz wedge dx. d omega is now 1 over 2 factorial partial z omega xy plus partial x omega yz plus partial y omega zx dx wedge dy wedge dz. Okay. So now the claim of Stokes theorem is if I do the left hand side of Stokes theorem says let me do this integration over d omega. Okay, so what I'll get is integral over the ball of 1 over 2 factorial partial z omega xy plus partial x omega yz plus partial y omega zx. And now I replace this by just an ordinary integration dx dy dz. There's only one coordinate patch, no partition of unity to worry about. Now the claim is that I can think of this as the divergence of a vector field, okay, where the components of the vector field are omega yz, omega zx, omega xy, okay. So omega xy being the z component, this being the x component, this being the y component. So I can write this as a divergence of a vector field dx dy dz. And similarly, now on the boundary manifold over this S2, I can write down the integration of omega over the boundary manifold. So on the boundary manifold, I do omega xy dx wedge dy, omega yz dy wedge dz, omega zx dz wedge dy. And this now looks like an integration. If I restrict to the surface of this sphere, that is over this surface, this is now an integration. So, I mean, if you imagine like faces of a cube, okay, this is the integration over dx wedge dy, okay, which is over the xy boundary, okay, where I keep z fixed, okay, and I integrate over the xy boundary, which is this one. Okay, and similarly, this is an integration over the yz boundary, okay, so where I keep x fixed, so that would be this one. Okay, so and of course I break it up into small area elements. Okay, and so basically what I'm doing is I'm doing the integration of v dot ds. Okay, so now basically the statement is that the integral of del dot v over the ball, okay, is equal to the integration of v dot ds, okay, over the surface. So this is Gauss's law. Okay, for example, divergence of the electric field, okay, over a volume is equal to the electric field integrated over the boundary, right? And that's how you get, you know, for a point charge, you find that the electric field goes as 1 by 4 pi r square, okay, in 3 dimensions. Okay, so this is basically, you can see that, you know, you get Gauss's law out of this generalized rule. Okay, this is true for any dimension manifold. So now you can even get Stokes law, okay, Stokes theorem, what you conventionally think of as Stokes theorem. So imagine like a 2-dimensional disk, okay, which we'll call a 2 ball, okay, B2, and this boundary which is in S1. So now on this 2-dimensional ball, I take a 1-dimensionless form. Okay, so omega is equal to a 1 form. So omega x dx plus omega y dy. I take d omega, which is partial y omega x times dy wedge dx plus partial x omega y dx wedge dy. So this is d omega, which I can now rewrite using the fact that dx wedge dy is minus dy wedge dx. I can write it as partial x omega y minus partial y omega x dx wedge dy. So now my integration over the ball is equal to integration of d omega is equal to partial x omega y minus partial y omega x dx dy. But this is exactly what you think of as the curl of a vector field, okay, dot dA, where the vector field, okay, so this is like the z component, okay, dot dA, okay, where the area element is dx wedge dy with, you know, with some particular orientation, okay. So this is like the curl of a vector field where it's a 2D vector field, and I've taken the z component of the curl. Okay, so it's something like this, and I've taken the z component of this. And similarly, the right-hand side of Stokes' equation is the integration over the boundary of this ball, which is the circle. Integration of the boundary of omega, which is the integration over S1 of omega x dx plus omega y dy. Okay, but this is exactly like saying that basically, if I imagine going around a square like this, omega x dx, okay, is basically v along this omega x along this, and then I integrate omega y when I, when I go this way, I integrate using omega x. When I go this way, I integrate using omega y. Okay, so it's like v dot ds. Okay, it's like the same vector, but now I integrate along the curve as I go along. So Stokes' law basically comes out of this. Okay, so the integral of del cross v dot dA, okay, over an area is equal to the integral of v dot ds along a line, or v dot dl. Okay, so over a closed loop, okay, this is the integration. Sorry, this is some area, okay, and this is the boundary of that area. Okay, the closed loop, which is the boundary. So basically Stokes' law and Gauss's law are just specific cases of this general Stokes theorem, which is that the integral over d omega, okay, of where omega is an n-1 form on an n-dimensional manifold, is equal to the integral of omega over the boundary of M. And a corollary of this is if M has no boundary, then the integral of d omega is just 0. Okay. So this theorem is useful not just for evaluating integrals over manifolds, but over submanifolds as well. Okay, so yeah, that's it. Any questions about this?
So
Yeah, go ahead, Prof.
sir, so we can do integration only for the orientable surface and
Only over orientable surfaces, yes, orientable manifolds. One important point is the boundary of an orientable manifold will also be orientable. So this will always, both sides will, if this is the left-hand side integration is defined, the right-hand side integration will also be defined.
Sir, while proving Gauss's law and Stokes's law, like the volume element or the area element that you define, like that was like how did you exactly write that as ds or dv?
This is clearly a volume element, right?
Yes, like I mean this is like our intuitive, like this we already know. I mean, so here also like we're stating that as volume. So I mean this. So what is the new thing here?
What is the new thing? Oh, no, what I'm saying is that I started with this. Okay, I started with just this rule. And I showed that a special case of this rule is Gauss's law, and a special case of this rule is Stokes' law.
Oh, yeah. I mean, that rule is now a general rule that you from there we.
Yeah, exactly. So I'm showing the laws that you already know, but I'm showing how you can get them from this new law, which is kind of more general.
Yeah. Yeah. Sir, and how does that corollary come? Like, if M has no boundary.
Well, roughly speaking, if it has no boundary, then the integral of the boundary vanishes, right? Like in the sense that imagine shrinking the boundary to 0. Okay. So imagine that I shrink this boundary to 0 size so that it vanishes, then basically the integration of the boundary vanishes. Actually, that's not the right way to do it. You can't continuously do this. Sorry, I should not say that you shrink the boundary to 0. Is that a corollary or is it just a different rule? I'm not sure. Okay, I'm not sure whether you start with this and prove that. Okay, this is just a rule. Okay, it has no boundary, then this is true. Okay, let me just stop the recording here.